Okay, so here are your work solutions for the Chapter 7 and 8 practice assessment. And number 1, we're evaluating a logarithm and also multiplying that by 10. So sidestep your 10 and try to evaluate log base 5 of 3,125. And 5 to the power of 4 is 625, and times that by 5 again. Looks like that's 3,125, so that means the first question is 10 times 5, which is 50. So just to be clear on that 5, I have in brackets there, of course, that's to evaluate that log. 5 to the power of 5 is 3,125, so the log is the power required here, and then that is 5. Don't forget to multiply by the 10 out in front, so that looks like letter D is the correct answer. Number 2, same kind of a deal, except we have to multiply log base 6 of 1 over 1296 by the number 9. So you should be asking yourself, 6 to what power gives me 1 over 1296? So of course some scrap work here, or just use your calculator, I suppose, works as well. 6 cubed is going to be 216. If I times that by 6 again, looks like we're in business, that's going to be 1,296. So this is 6 to the power of 4 in the denominator. So of course in brackets here, to get a reciprocal of that 6 to the power of 4, we need a negative power. So that log is going to be negative 4. Of course, going to times that by the 9 out in front. And we get an answer of negative 36, which is a letter D. Okay, and now numbers 3 and 4 are probably a little bit easier, but keep in mind you can use your calculator, of course, for this online assessment. The numbers are big enough there that probably warrants it, but I did struggle to get through it and got the correct answers. For this one, is just taking advantage of your identity that if you see 2 raised to a power of a log with base 2, all that business, I guess after the negative 3, and I guess before the plus 6, 2 raised to that log base 2, the exponential erases the log, and you're left with the input on that topmost, in the logarithm, in the exponent. So this is going to be negative 3 times 31, which is negative, 93? Negative 93 plus 6. So I guess we're looking at negative 87 for part, I guess selection E there is the correct answer. And then similarly for number 4, this is, I guess, a base E logarithm, of course, but it is trapped inside a base E exponential, so the exponential wipes out that logarithm. You're going to be left with 31 after the multiplication by 8 and before that subtraction of 2. So it's going to be 248 minus 2, which is 246, the correct answer, letter A. And now we're into some more log properties, specifically for, I guess, the next 2 questions here, where we have to expand this log base x of 70, first of all. So, of course, we're going to factor 70. I guess we can do that separate from the log for the time being. That is 7 times 10, which, of course, is 2 times 5 times 7, I guess in ascending order there. So factor the 10 into 2 times 5, and don't forget the 7. There's the prime factorization, so we can split this product up now into 3 separate logs, all added together. So log base x of 2 plus log base x of 5 plus log base x of 7, and hopefully we have all 3 logs above, and we do. So the log of 70 of the product of those 3 factors is going to be the sum of these 3 logs, and it'll be 0.6 plus 1.5 plus 1.8. And again, you can use your calc here, but this isn't too bad. That's 3.3, adding the last 2 together, and another 0.6, so 3.9, which means the correct answer is C. And similar to question 5, we have another log property question where, again, we just have to factor, I guess, the numerator there, 15. I guess I can write it all out as a log. This is 5 times 3 in the numerator, all over 2. And now we can expand this out into log base x of 5 plus log base x of 3. Of course, those two factors are in the numerator. And in the denominator, we have a 2, so we have to say subtract log base x of 2. And the other way, of course, you could do it is go log base x of 15 minus log base x of 2, and then split up that log base x of 15 into those two pieces. And it would be nice if we had all three logs above, but we got at least two of them. We have 0.8. And after the subtraction, we know our log base x of 2 is 0.4, so we have to work a little bit to figure out what log base x of 3 is. And of course, we're going to use this. This is log base x of 3 squared. And we know that's 1.2, so we're going to use a property of the logs, the power property, where that 2 can come down in front. So this is going to be 2, equivalent to 2 log base x of 3, equaling 1.2, and now divide both sides by 2, and we know that log is going to be, I guess, 0.6, ignoring the decimal, and 12 over 2 is 6, and then stick in your decimal. So we have to put a 0.6 in here. And again, if you're having problems with the arithmetic, I'm sure you won't have problems, but if you feel like it's taking you too long, of course you can use your calculator for some of these things. And we get 1.4 minus 0.4, so it looks like the answer is 1, I guess decimal 0 in terms of sig fig accuracy, but the closest thing we got to that is, of course, just the number 1 there, which means letter D is the correct answer. Okay, the next couple of questions are dealing with the graphs of log functions, and since this is a multiple choice format, let's see if we can take advantage of that a little bit. First thing to consider with this log function, it's a base 4. And there's no reflection, so this will be our more typical log shape where it's going to have a vertical asymptote somewhere. So that would be the shape I'm looking for. Already I'm looking at B and D as possibilities. Next thing to keep in mind is, based on this x plus 4, of course this shape should have been translated 4 units to the left. Or its vertical asymptote, of course, is located at x equals -4. And I look at that and say, well, that's not going to happen. That's at +4. This one is starting to look good. And of course, you might be considering these and say, how do I know it's not these? Well, this is a reflection. It looks like it would be a log function reflected across the y-axis. So you would need a minus inside in your input there in front of that x plus 4. And this is, of course, an upside down log. So this would be a logarithm reflected across the x-axis, or another way to interpret that, a log with a base 1/4. So that is letter D is the correct answer here. And if, again, you feel that that is a little wishy-washy, you could plot some points, I suppose, just to verify that you did pick the correct option. So if we put x equals 0 in here, notice if I sub in x equals 0, we'll get a y value. Looking at letter D, it better be a y value of 1, so this will confirm if we're correct. So if I go log base 4 of 0 plus 4, of course that's log base 4 of 4. There's 4s everywhere here, but this is going to be 4 multiplied by that logarithm. Subtract 3, and of course that's an easy log to evaluate. 4 to what power is 4? That power is 1. So we get 4 minus 3, which definitely looks like is the correct ordered pair on this graph. So not that we need it to be, but I guess we're now doubly certain that D is our correct answer. Now number 8, just a little bit tougher. Here's where we got to use this graph and try to figure out, of these 5 options here, which is a lot, it seems, which one of these equations is the correct equation of this. So again, this is our typical log shape, which means I shouldn't see any reflection, so I can start to rule out C and E at this point. And another thing you can do, of course, is to be aware that your vertical asymptote is at 1, 2, 3, 4, 5, 6. I should say -6. So I'd be looking for, I guess in a lighter color here, to be looking at these plus 6s. So right now I've narrowed it down to 3 options, and keep in mind it can't be this one because there's a minus out in front. So I guess we're down to a 50-50 chance of being correct, but let's just try to be a little more thorough, I suppose, instead of just ruling out the possibilities in this multiple choice format. Remember, we're looking for a spacing of 1 unit from our vertical asymptote, which means right here is where we need to be looking at for our pretend x-axis. So that means this log function, whatever it is, we know it's been translated 6 units left, but now we know it went down 3 units. Been translated down 3 units. So you can start to see I'm getting really confident that it's either one of those first two options. But of course, let's figure out the base, and if we can find one step above that, right, above this, I should say, pretend x-axis, which seems to be happening right here, even though this grid is pretty teeny tiny. This is going to be our base, is this horizontal distance, which looks like it's 2 boxes. Okay, so the base has to be 2, so that means B is the correct answer here. And if you don't like the process, I guess, that I used there, then of course you could just take any ordered pair. And I guess this one is as good as any. That's 1, 2, 3, minus 4. So I'll take the ordered pair minus 4 and minus 2. And we could sub it in to our, I guess, incomplete equation, logarithmic equation, where we know it went 6 units to the left, and we also know it went 3 units down, and we can solve for our base, and we'll also confirm that the base is 2 here. So when we sub in y equals -2, we're going to get log base b, write a little neater here, log base b of inputting -4 into that input of that log. This gives us -2 equals log base b of 2 minus 3, and I'm running out of space, so I guess I can squeeze it in. We'll add 3 to both sides, and if we add 3 to both sides, I'll just erase that. That's going to give me 0, and adding 3 to -2 gives us 1, and then we have a really easy log to evaluate. The base required here has to match that input, so our base is 2, or go to exponential form. The base to this power of 1 must equal the input, so we know our base is 2. So of course we already knew this, but now we've doubly confirmed that our correct answer here is letter B. And now down for the last one, the last graphing question. I'm sure you won't be upset by this. We can start to see this is either a fractional base, and I don't see any options, but I see an upside down logarithm, so that's I guess kind of important to be aware of. So we can reduce it down to 3, options. It would have to be to choose from. There's 2 that we can rule out right away. But I think we'll be a little more rigorous here, just like the previous example. If you find your distance of 1 from your vertical asymptote, this tells you that this function would have been translated up 3 units. So right away, I know my function has to be of the form log base b, I guess we'll say y equals, log base b of, and it also went 1, 2, 3, 4, 5 units to the left because of the vertical asymptote that's there. So 5 left and 3 up because of our pretend x-axis. And of course, here's where we can sub in another ordered pair, which of course 0 and 1 is the other ordered pair, the y-intercept, and we can solve for a base. And if we get a weird base, use a change of base to either match base 4 or base 5 here. But let's look at the other shortcut, because you should be able to use that now. This distance here is our base, is the shortcut. So that's 1, 2, 3, 4, 5 units. So my base must be 5. I'll just say base is 5. And this other distance here is the vertical stretch that's involved. But of course, you'd have to be on your toes here to know that this function has been reflected upside down as well. So let's look at this shortcut. And I think I don't want this video to be too long, but if you're not really certain of this, substituting the x and y value might be just as safe as what I'm doing here. So that looks like a stretch by a factor of 2. So I'll write my shortcut answer over here. Of course, it's not just a stretch by a factor of 2. We need this log to be upside down, because it's an upside down shape. And then my base has to be 5. I guess I'll color code this. Base 5. Try that again. Base 5. And of course, my translations stay the same. Okay, so that's one way of getting your answer. Now let's go in and do our substitution, I guess, where we'll put y equals 1 and x equals 0, and see if we can make sense out of this equation, logarithmic equation. And if it's a weird base, as always, we'll just do a change of base. And I'll get that little blotch off my 0 there too. Okay, so what do we got? We got 1 equals log base b of 5 plus 3. So we'll subtract 3 from both sides. We'll get negative 2 equals log base b of 5. And now we'll go to exponential form just right here. That would mean b to this power of negative 2 has to equal 5. And we can raise both sides to the power of negative 1/2. And we'll get b to the power of 1 equals 5 to the power of negative 1/2. And that is definitely a messed up base. And that negative is hardly visible there. So this is the base we're going with. So like I say, this is a much harder way of doing this question, but I think we'll suffer through and see if we can wrap it up. So I guess you could write that as 1 over the square root of 5, but I think I'll just keep that as 5 to the power of negative 1/2. We don't need to go to radicals. And like I say, I think this is probably the hardest way of doing it, but I guess if you look through the options here, it wouldn't make any sense to be trying to go to base 4. Maybe as an act of desperation to say, okay, right now, just to be clear where I'm looking, right now it looks like we got this messed up base that's 5 to the power of negative 1/2. Let's do a change of base in here and see if we can match one of these options. So we'll go base 5 log top and bottom. And of course I'm going to keep my x plus 5 input on the top. I've got a lot of space here, but I think you can still read this. And then I'm going to go 5 to the negative 1/2 on the bottom. You realize you have an identity down below here. 5 to what power is 5 to the power of negative 1/2? Well, of course, negative 1/2 is your answer. So we are dividing by negative 1/2 after we evaluate that log. So this actually didn't take too long, because I didn't bother trying to mess around with radicals. And dividing by negative 1/2, of course, is the same thing as timesing this by negative 2. So we'll erase all that. It's a little messy, but here's our answer. I guess I can line that up. Here's our alternate, I guess, method. Of course, hopefully giving us the same answer, not minus 2, log base 5 of x plus 5 plus 3. Now, which answer is it? We don't want to choose the wrong one after all that work. It looks like it's going to be letter A, but letter C looks so darn close, so better make sure that I didn't pick the wrong one. And it looks like I almost picked the wrong one because I was so busy looking at the other pieces of information, I accidentally forgot to check the base. So lucky, I salvaged that one. Letter C is the correct answer. That's minus 2, x plus 5 plus 3, and yes, with the base of 5. Okay, so now we're into the number theory questions on this assessment where we're trying to determine the number of digits in this ridiculously big product. So remember, the whole notion is if you take the log of that number and don't forget to apply the floor function to it, so the log of that product, and add 1. So we've looked at this in some detail, and actually a lot of detail in class. This essentially is just a way, if you take the log, ignore the decimal since we're only dealing with positive numbers here. This is called the floor function. And don't forget to add 1 to get the correct number of digits. So we have to figure out what the log of this product is. That's 2850 multiplied by 17. I'm not sure why I'm taking up a little space here, but anyway, 17 to the power of 800. So let's start expanding all this inside the log. So we're going to go log, and of course these are base 10 logs, which I don't have to write, but maybe I should, but these are base 10 logs because of course we're working with the base 10 number system here. So log of 15 to the power of 2850 plus log base 10 of 17 to the power of, now more visible, 800, and once I take the floor of that I can add 1. Now, of course, I can't enter this into my calculator until I take advantage of the power property here. So this is going to be 2850 multiplied by log base 10 of 15 plus 800 multiplied by log base 10 of 17. Ignore the decimal on that and add 1, and you will have the correct number of digits. Okay, so here we are in our calc. 2850, and I better type that in correctly, 2850 times the common log of 15, don't forget to close your bracket, plus 800 multiplied by the common log of 17. And I will look at that number for a second and ignore the decimal. So 4336. And I guess we don't need the calc to add 1, but 4,337 is the correct answer. So we're looking at letter C as our final answer. Okay, so write down that correct answer of C and move on to number 11, which is very similar to question 10. Except now you're applying the floor function to the log of this quotient. So this question, the setup would be almost the same, except now you have not a product inside this base 10 log, but of course this is 12 to the power of 3,350, all divided by 13 to the power of 1,100. So of course, floor function that and add 1 to get the correct number of digits. So we're going to expand this out. First step is to write this as the difference of two logs. And both of these are common logs. So log of 12 to the power of 3,350 minus, now this is all in that log if you're not sure. Next one would be after the subtraction and this difference, log base 10 of 13 to the power of 1,100. And that's all inside our floor function, and don't forget the plus 1. So of course, just like last time, we can't evaluate any of this on our calculator. We'll get overflow errors until we use our product property, our power property, and move that power down in front. So this is equivalent to 3350 multiplied by log base 10 of 12 minus 1,100 multiplied by log base 10 of 13. And take the floor function of that difference and add 1, and we'll get our correct answer. Okay, so this time we have 3350 times the common log of 12, subtract 1,100 times the common log of 13, and we'll ignore the decimal and say 2389 plus 1 for a final answer of 2,390. Okay, so penciling in our correct answer, letter D, 2,390, as we move on to our last number theory problem. And this one involves logs yet again, which is probably not surprising, just in a slightly different way. So we need to figure out an integer or integers k such that when we raise the number 3 to that number k, we get exactly 7,800 digits. So the setup here is we need to make sure that 3 raised to this power of k is in between a couple of powers of 10. Now, a number that has 7,800 digits actually is 10 to the power of 1 less than that. So 7,799. So subtract 1 from that. Yeah, that'll be 7,799. So this is 1 with 7,799 zeros, which is actually a 7,800 digit number. And then we can allow 3 to the k to be equal to that. And then if we actually just add on 7,800 to this power, this is 1 with 7,800 zeros, which is 1 digit too big, so no line under that inequality. And now we apply logs to everything in this inequality because everything is positive here, our base and our exponents, so we can take some liberties with our inequalities and we don't have to separate this into two different cases. So of course I apply log base 10 to this base 10 exponential, and we can probably guess what's happening to that. We're going to be wiping out that exponential. We'll have to do our power property in the middle here as well, and then of course log base 10 of 10 to the power of 7,800. So those base 10 logs wipe out the outer exponential base 10s. So now we have a log of our number, I guess of 3 to the power of the number we're looking for, is stuck between these two numbers, 7,799 and 7,800. Now, of course, our power property here, we're going to take that k down in front, the next step, and this will be k multiplied by log base 10 of 3, and since that's a positive number, we can divide everything by log base 10 of 3. And I guess we can write it down in here as well, because if we do that, of course, those things will divide in evenly and cancel off, and k is in between these two numbers. So we'll look at these two numbers on our calc and make sure we take integers that fall, I guess, equal to this or greater than, or I should say greater than or equal to this number, but make sure we don't actually include this number. And I'm glad I caught that. I just noticed I accidentally included my line on that inequality, which is a no-no, because if we include this, then we'll be one digit too big. Okay, so typing this into our calc, 7,799 divided by log of 3, check that number, and then 7,800 divided by log of 3. We need to pick all integers in between these numbers. Of course, it can be equal to that number. Well, since it's not an integer, that's not an issue. We can pick anything bigger than 16,345, and of course that will start at 16,346, and we can go up to, but not go past or even include this last number. And of course this one's a little tiny bit bigger than 16,348, but we can still include 16,348. So the correct answer is going to be from 16,346, 47, and 16,348, which looks like it's letter D is the correct answer. Okay, so we'll pencil that in, letter D, and we move on to something that's not number theory. We have a single inverse equation question. So we need to find the equation of the inverse of this logarithm. It's a little bit less abstract, I think, potentially. So we'll get rid of the function notation. I guess I can go down here. We'll say y equals 2 times log base 5 of x minus 4 plus 10, so not much happening in that first step, just essentially tossing out the function notation and rewriting the problem. And now we'll get our log by itself first, so we'll say y minus 10 is equal to 2 times this logarithm, base 5 of x minus 4, and then we'll divide both sides by 2, so we'll have y minus 10 all over 2 equals log base 5 of x minus 4. So I think I'll just go up here and continue my writing so I can see my options here. So we now have, I guess, the key step in all this exponential logarithm business is to rewrite this in exponential form, which is to recognize, I guess I'll say continued here, which that should be obvious. If we recognize our base is 5, then 5 to this stuff over on the left, this is the power. Remember, that's what our log is equal to. This is going to be y minus 10 all over 2. So 5 to this power must equal x minus 4. So we'll have 5 to the power of y, subtract 10 all over 2, plus 4 equals our x. Of course, just adding 4 to both sides. Now let's swap x and y. I guess I'll write y on the left-hand side. So y equals 5 to the power of x minus 10 all over 2 plus 4. And we'll scan through the possibilities here, look for x minus 10. And I think that's the only one we have. So that is 5 to the power of x minus 10 all over 2 plus 4. So letter C is the correct answer. Okay, question 14 is a doozy of an exponential equation. The reason it's, I guess, we've got these kind of complicated looking options here. It's because we get two different bases in this exponential equation. We don't just simply have an exponential function equaling a constant. We have a base 3 exponential that's been transformed, that 4x minus 5 business in the exponent, and we need to figure out how that is equal to a base 5 exponential with a again, transformed base 5 exponential. And we need to write our answer in the form of using 3 logs. And note, since there's no bases indicated there, we would assume that, of course, common logarithms are what's required to use to get the correct option here of A, B, C, and D. And we're also told that the arguments here, m, n, and p, are positive integers. Remember that capital set is a set of integers, and the plus here just indicates we're working with positive integers only. So it means we start rewriting out our exponential equation and applying common logs to both sides. So we'll say log base 10 of 3 to the power 4x minus 5, and that's all inside that common log. And on the right-hand side, we're, of course, applying the same logarithm, a base 10, which I guess I'll write out a few times, that base. And so that's a log base 10 of 5 to the power of 2x. Now, of course, why we did that was to get access to our exponents. Both of these exponents are going to come down right in front with the product property. I'm sorry, again, I'm saying product, the power property, the other p word. Powers come down in front, so this will be 4x minus 5, and I'll enclose that in brackets. And that's going to be now multiplied by log base 10 of 3. And then on the right-hand side, this 2x will come down in front. I don't need brackets on that. That's just a single term, and that's being multiplied by log base 10 of 5. So what makes this, I guess, such a messy situation, and the answers kind of tell us that is the situation here, is because there's x's on both sides of this equation now. So our only option is to expand out this left-hand side, and so we'll write that out as 4x multiplied by log base 10 of 3. And then we have a minus 5, or I should say subtract 5, multiplied by log base 10 of 3 again. And then simply just recopy the right-hand side. Nothing to do here yet. So that's going to be equal to 2x times log base 10 of 5. So we're getting all kinds of logs. We now have, I guess, 3 different logs in our equation. Now, I guess 2 of them are the same right now, but let's not worry too much. We'll sort things out here and hopefully get 3 unique logarithms in our final answer. So what's left to do now? Well, we have to get x by itself and isolate it. Now, since I have a term with x in it here, that 4x term, we have a 2x over here. We have to do some sorting and get everything with an x in it over to the left-hand side, or any side. I think I'll just choose the left-hand side. So we'll say 4x log base 10 of 3. So I'll subtract this 2x expression from both sides. That'll be minus 2x multiplied by log base 10 of 5. And then I'll also add this. This is just a number, a constant. I'm going to add that 5 log base 10 of 3 term to both sides, and it will show up now over on the right as 5 multiplied by log base 10 of 3. So now we're getting somewhere. I now have my x's together, and there's an x in this term, and there's an x in this term, and of course we need to factor out that x out of both of these logarithms. And when we're done with that, that's going to be equal to, well, x times this product is going to be equal to 5 times log base 10 of 3. So I think we're getting there. A couple of more steps left. So when I take out this x, I'm going to be left with 4 times log base 10 of 3. And then minus 2 times log base 10 of 5. So now I have x by itself. Now I can divide both sides of this equation. Come up here a little bit. Both sides of this equation by that really messy expression, which is the difference of 2 logarithms. So on both sides of this equation, this is going to be quite long. I don't think I'll write the whole thing out again. We're just going to stick 4 log base 10 of 3 minus 2 log base 10 of 5 on the bottom. And of course, by doing that, by dividing both sides, this whole thing is gone, and this is what x is equal to. Now we're getting close. We now have to recognize I don't see any 5s, 4s, or 2s in front, so we have one last step to do, and of course is bringing this coefficient inside. To each of those, bringing each coefficient inside to the argument in the log, and of course they become powers once we bring them back inside. So the last step here, I think I'm just going to go with one color because this is kind of time consuming with all the switching. We'll say this x is equal to log base 10 of 3 to the power of 5 now. We'll figure out what that is in another second. And on the bottom, bringing that coefficient back inside as a power, this will be log base 10 of 3 to the power of 4, subtract log base 10 of 5 squared, where that 2 comes back in. Okay, so hopefully we can recognize now 3 to the power of 5, one of these options up here. 3 to the power of 5 is the number trapped inside that top common logarithm, which is 243. I guess you can cheat and look up there, but you probably still should check with your calc. And then we have log base 10 of 3 to the power 4, which is 81. And then minus log base 10 of 5 squared, which is 25. So we have 3 common logs, and if you're wondering what that m, n, and p business was all about, well, our m is that 243, the n is the 81, and the p is the 25. We have our subtraction, and I guess if we look at the options, be careful which one we pick. We need the one with 243 on the top, positive 80, or 81, I guess, in the positive log, and then after the subtraction, 25. So, of course, this is our correct option. And that means D is the correct answer. Okay, number 15, we have a log equation again. We now have 2 times log base x of 17x equals 18. So, of course, we have x's in 2 different locations there, which probably should cause you a bit of concern. But let's not panic. We're going to just take this equation and let's divide both sides by that 2 that's in front. So I guess I'll quickly rewrite that out, but not much happening here other than getting a bigger and greener version of this equation. Divide both sides by 2, and that's going to be 1, and 18 over 2, of course, is 9. So by doing that, single log equaling a number, we can now go to exponential form, where, of course, remember our log is the power, the exponent, so that should become the exponent when we move into exponential form. This is clearly our base, so this is going to be x, a messy x to the power of this 9. I guess I'll just write it that way. This must equal 17x, of course, the input in the logarithm. And if that red box is actually helpful, I guess I'll include that as well. So the exponential version of this logarithm is x to the power of 9 equaling 17x. So you might be asking yourself, how am I supposed to solve this? Well, everything has an x in it, so usually the play is move everything to one side, and other plays don't change the numbers. Make sure you write a 9. I don't know, I guess part of the box I'm reading that as a 19, but anyway, it should be x to the 9 equaling 17x, so of course we'll subtract 17x from both sides and at least accomplish something in this step other than getting rid of my confusing red box. So everything has an x in it, so instead of dividing by an x, the best play is to use a common factor here. So we can take a common factor of an x out of both of those. Now, of course, if this second term had a higher power, we could take a higher power of x, but since that was just a linear term, 17x, the biggest power of x we can take out is x to the power of 1, which means this will become x to the power of 8, and this is minus 17. So x times x to the power of 8 minus 17 needs to be equal to 0. So, of course, we'll set up our 0 product property here. How do we make x equal to 0? Well, x equals 0 will accomplish that, maybe not surprisingly. And a little bit more work to do here. How do we make this x to the power of 8 expression equal to 0? Well, that's a good question. Let's set it equal to 0 and go through our 2-step procedure. We'll add 17 to both sides, and then we'll try to get rid of that power. Now, since this is an even power, even powers are the nasty ones when you're working with expressions like this. It actually requires a plus or a minus root. And don't write a square root, it's an 8th root. So the plus or minus 8th root of 17. So it looks like we have 3 options here. X is 0 and x is plus or minus the 8th root of 17. And of course I'm favoring radicals here. If you're wondering why I'm using a radical and not a power of 1/8, of course the answers seem to have eighth roots in them. But before we're done with any log equation, you got to go back and double check and make sure you understand the restrictions that are on your logarithm. Well, our base can't be negative, and it can't be 0, and it can't be 1. 17x can't be 0, and it can't be negative. So I guess the most obvious domain restriction here, stick that up here, get a pen, with our original equation is that x must be greater than 0. And I guess if you want to tack on, x can't be equal to 1 as well, but that's not relevant here. We didn't get any x values of 1 in our answers, so can't be 0, so that excludes that. And of course it excludes, I guess, the negative part of that, I guess the negative option from our x to the power of 8 equation. So the correct answer is simply going to be x equals the 8th root of 17, which it looks like letter C is the correct answer. Okay, finally, the last question, number 16, another logarithmic equation, and we're at the 40-minute mark, so it should be telling you that your online assessment's going to take you in the 45 to 60-minute range. So let's finish off. So to deal with a logarithmic equation, of course, there's two different logs, and they're both base 2. We'll condense that left-hand side, and of course, we'll still have that equal to 4. So if we have a sum of two logs, we can condense that down to a single log. And inside this log will be the product of those two inputs, or those two arguments, 3x plus 8 multiplied by 7x plus 5. So I'll just square brackets just to make sure we're clear. That's all inside now, a single logarithm. It's been condensed, and this is still equal to 4. And of course, let's get rid of our logarithm by going to exponential form, where our base is clearly 2. And this 4 over here is our power. So this log equation written in exponential form is 2 to the power 4 equals the stuff inside the log, which is 3x plus 8 multiplied by 7x plus 5. So it's kind of a nasty quadratic we have here, but this is 16. So we'll do that at least in this next step, and we'll start expanding this out. This is going to be 21x squared, and here's our quadratic expression. We'll get a 15x, and then we'll get a 50, ooh, I forgot the x. And then we'll get a 56x, and then finally we have a 40 plus 40. So let's clean this up, and of course, since this is a quadratic equation, we'll get a 0 on the left-hand side, or at least a single side. 0 probably makes the most sense because everything seems to be on the right here. Well, if 0 equals 21x squared, adding these together, we get, what, 60 and 11, we get plus 71x. And then 16, I guess 40 minus 16, which is what, 24, positive 24. Adding those, we get 30 and 10, which is 40. Now, if I didn't have these options sitting in front of me here, I probably wouldn't even entertain trying to factor this, to be honest with you. The numbers are kind of big and awkward enough that I think your most efficient approach would probably just be to use the quadratic formula. But since we see, or at least I see, some 8 over 21s and some 3s, I'm going to obviously assume that this is factorable. And I'm going to try just to use a 21x multiplied by an x. That's going to obviously give me 21x squared. And if I see an 8 here, it probably makes sense that the 8 should go there. Right? Everything's positive, so it also should make sense that if we factor this, everything has to stay positive. So 8 times what is 24? I think this is the factored version of this. So I guess we would have been searching for two numbers that add together to give me 71 and multiply to give me 21 by 24. Yeah, like I say, not very user-friendly if you're trying to factor it, but the multiple choice options actually make it pretty easy. So let's check to make sure this does work. I get 21x squared. I get 21 times 3x, which is what, 63x. Let's keep track of the x terms over here. I have an 8x, and then I have 24. And if I add those together, I get 71x. So it worked. It's factorable. Like I say, if it wasn't a multiple choice option, quadratic formula is definitely the play there. So now, zero product property. What makes 21x? I guess we can color code that. What makes 21x plus 8 equal to 0? Well, of course, solve this little linear equation. And then the other Potential solution is what makes x plus 3 equal to 0. Well, that one's pretty easy to solve right away. That's in x equals negative 3. And here's our two-step linear equation. Subtract 8 from both sides and then divide by positive 21. So you should be getting x equals negative 8 over 21. So we're seeing these numbers occur up here, I guess, as options in our, 6 multiple choice options. So which are the correct ones? Of course, we have to go back and kind of analyze and worry about our domain. And we'll look, I think, at the domain of each of these logarithms. So we need to avoid 0 and negatives in both of these logs, which means 3x plus 8 must be greater than 0. And if I, again, just like we did with the two-step linear equation down here, we can do the same thing with this inequality. Since we're going to be dividing by a positive number, we can subtract 8 from both sides and divide by 3. So we need to make sure our x values are greater than minus 8 over 3, which of course is negative 2 2/3. So that disqualifies this as an answer. It doesn't work in that first logarithm. And what's more, it probably doesn't work in the other one as well, because the second logarithm in this equation would have a domain restriction of 7x plus 5 being greater than 0 to avoid negatives and 0 in the input of that log. And of course, subtract 5, divide by positive 7. This inequality stays a greater than, x greater than minus 5 sevenths. Of course, negative 3 is not greater than negative 5 sevenths as well. So obviously that's a little bit less than 1. So you might want to check this, of course, on your calculator to make sure that this x value is a little bit to the right of minus 5 sevenths on your number line. It's definitely a whole lot to the right of negative 2 2/3. So it looks like this is our answer down here. The nice pretty pink box on it, negative 8 over 21, which is letter B, because that is the only x value of our two possible answers that works in both of these domains, or I should say exists in both of the domains of the logarithms that are in this logarithmic equation.